Good morning, lecturer and fellow classmates. Today, I would like to present my project Part A. I review 4 research papers related to computer architecture. The first paper discusses a memristor-based accelerator for transformer modules. It performs computations directly inside memory, which reduces energy consumption and improves processing speed. The second paper introduces a hybrid process in-memory accelerator for GPT models. By combining memory and computation, it reduces data movement and improves efficiency and scalability. The third paper presents a programmable crypto processor based on the RISC-V architecture. It supports post-quantum cryptography and helps protect future systems against quantum computing attacks. The fourth paper focuses on secure services for RISC-V architectures. It improves system security through memory protection and isolated execution environments. In conclusion, these papers show that future computer architecture will focus on AI acceleration, energy efficiency, and cybersecurity. Through this project, I gain a better understanding of how hardware design can improve both performance and security. Thank you for listening.
Welcome to this brief overview of SMP cache, an educational, stress-driven simulator designed to evaluate cache memory performance within symmetric multiprocessor environments. SMP cache provides a practical, visual way to study cache coherence. Users can observe exactly how architectural configurations such as cache size, block size, mapping technique, and replacement algorithms. This will affect overall system performance. By using real program memory traces, it demonstrates how protocols like MESI manage data consistency across multiple processors sharing a common main memory. To implement a simulation project, we will need to open a simulator and click the configure to adjust settings for the multiprocessor, main memory, and cache. We will open a memory trace to load my component. Once ready, we can choose any simulation to run, such as multiprocessor, cache, and memory block evolution. Here our simulation process, 28,015 total access across 4 processors, consisting of 21,562 instruction fetch and 1,966 data reads, 4,487 data writes. And then following an initial spike in compulsory misses, performance stabilized rapidly at a steady 90% period and a 9.6 miss rate, showing excellent data locality. Finally, we observe a massive delayed synchronization, which is our final drawback before. Our configuration resulted in a significant 180 final block transfers. The final writebacks were heavily concentrated in cache 3. This means the system had to perform a massive final writeback sweep to update the main memory with these locally modified dirty blocks before halting.
So good morning, good afternoon, and good evening, everyone. So now I'm going to show about the part C, which is version control system with GitHub. Git is a distributed version control system developed by data developers. It is used to track change in source code and maintain different versions of a project. GitHub is a cloud-based platform that hosts Git repositories, while Git manages version history locally. GitHub allows team members to collaborate online. In this project, the repository was created by the group leader and collaborator were added. Team members can clone the repository, make changes, commit their work, and post updates to GitHub. Git provides many benefits such as version tracking, collaboration, backup, and rollback. This feature help developers manage source code more efficiently. In conclusion, Git and GitHub are important tools for collaborative software development and project management. So now we go through how we change the commit. So you can see the member text is blank. I edit the file and add my name and commit the change. Let me refresh. So now you can see there's my name at here. So that's all the GitHub, and thank you all.
Hello everyone, I'm Kuhan, and to wrap up our presentation, I'll be summarizing the overall impact and key conclusions we've drawn from this assignment. Overall, this project successfully bridged the gap between theoretical computer architecture concepts and practical real-world implementation. By dividing the work in three distinct parts, we gain a highly well-rounded understanding of modern computing. In Part A, reviewing research papers open our eyes to how emerging memory technologies like memristors and PIM accelerators are optimizing heavy AI workloads, and why hardware-level security is so crucial for RISC-V architectures. In B, SMP Cache Simulator gave us hands-on experience. We were able to visually observe how cache coherence protocols, specifically MESI, directly impact system performance, miss rates, and burst traffic. Finally, in Part C, we stepped into the practical side of collaborative development by learning to use Git and GitHub. The difficulties and benefits. Of course, this project wasn't without its challenges. Initially, grasping the dense technical details of the advanced hardware research papers was quite demanding. Additionally, transitioning to a GitHub workflow presented a learning curve for us. We had to figure out how to properly navigate cloning, pushing, and even deal with missing repository email invitations. However, the benefits outweigh the initial hurdles. Implementing Git ultimately kept our group highly organized, ensuring we could work simultaneously on the same repository without accidentally overwriting each other's files. Ultimately, this project drastically improved our technical research skills, our teamwork, and our practical knowledge of both hardware simulation and software version control. Thank you all for listening.